Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics. We're going to be taking a look at Rutherford's model of the atom and how that transitioned to a quantum model of the atom, which was named after Niels Bohr. So we'll start out with Rutherford's atomic model, and what it did was it mimicked a miniature solar system. So the nucleus was like the sun, the electrons orbit around the nucleus like planets orbit around the sun. Gravity provides the centripetal force in the solar system. The Coulomb force, the electrostatic force, provides the centripetal force in the atomic model. And people loved this model. It was very understandable, very scalable, but it also had two significant problems. So here are the problems with the Rutherford model. First of all, the electrons are accelerating. And we know in classical mechanics that accelerating electric charges produce electromagnetic waves. So therefore, the electrons going around in circles should be giving off electromagnetic waves. Electromagnetic waves are energy, so they're giving off energy, and they should spiral into the nucleus. That means all matter would collapse, and in fact, all matter would collapse very rapidly. And therefore, Rutherford's model, although it's a good starting spot, isn't a stable model of the atom. So it turns out that working with Ernest Rutherford was a young physicist, a theorist named Niels Bohr. He certainly knew about the Rutherford model because he was working there, and he said, well, it's got a lot of good stuff in it. Let's add some quantum theory to this to make the model stable. So he made three assumptions. The first one was only certain orbits are allowed, and in hydrogen, and he went on, and Bohr's model originally was just for hydrogen and hydrogen-like atoms. He said only certain orbits are allowed, those with which the radius of the nth orbit, whichever, the radius of the fifth orbit, for example, are going to be the radius of the first orbit times n squared, where n is the orbit number, so in this case it would be 5, and the radius of the first orbit is 5.2 e minus 11 meters. So if you want to figure out the radius of the fifth orbit, you just say it's the radius of the first orbit times 5 squared, or 25. He also went on to say that the energy of any orbit is equal to the energy of the first orbit, this time divided by n squared. And we give the energy of the first orbit a value of negative 13.6 electron volts. The second and third assumptions go like this. We're saying that for number 2, electrons in allowed orbits don't lose energy, just a statement of fact. They're not going to give off electromagnetic waves. And number 3, when electrons change orbits, the photon energy emitted or absorbed is going to be equal to, and we've got here, E of the photon is equal to E of the initial orbit minus E of the final orbit. So we're going to do a quick sample calculation for this right now. We're going to calculate the energy for a D to B transition in mercury. In order to do that, you've got to get your reference table, and we've got some energy level diagrams for hydrogen and for mercury. We're looking for the D and the B level in mercury. So the D level is negative 4.95 electron volts, the B level negative 5.74 electron volts. So I come back to my calculation. Energy of the photon is negative 4.95. That's where we started out, minus negative 5.74 electron volts. And then the energy of the photon turns out to be plus 0.79 electron volts. And we've got a little note here. The plus sign means that the photon was emitted or given off by the atom. A couple other things we could calculate with problems of this type. We could say, what is the frequency of this photon? We're not actually going to do the calculation at this point in the year, but if we were going to do it, the first thing we do is convert the electron volts that we have up here to joules. That's in the front page of your reference table. 1 electron volt is 1.6 E minus 19 joules, and then we use the equation E equals HF, and we could use that to calculate the frequency. We just solve for F. That's our introduction to Rutherford and Bohr model.